Good evening to all my fellow members of class 504. I'm Logesh Balamani, and today I'm presenting based on the assignment 2, which was given to us and assigned to us. And the topic for my assignment today is based on the subject of LEDs. So I have searched on 3 journals and thesis papers based from the year 2015 all the way to 2020 up to now. And without much delay, I think I will go moving forward. I'll just go to the next page and let's discuss on the 3 topics of the topic on LED as we have today. Thank you. Okay, moving forward now with this page, here are the 3 topics which I will present today. These are the 3 journals which I will present today. Before even moving further, actually, I would like to explain a bit on these 3 journals. So we are well known from the first page that the topics I will be covering today is LED. Now, moving forward, when I talk about LED means I would like to talk about the material science which is used in producing LED. And one of these material which we are talking about today is the phosphorus. So I believe that many of us in our class 504 are well aware upon the function or the nomenclature of LED. So what I'm talking today is very much on the material or the BOM of producing an LED, which is the phosphorus. And here, talking about phosphorus, I'm going even deeper, where I'm talking about producing YAG doped cerium phosphorus. Basically, my paper talks very much on the process making and the synthesis of producing YAG cerium based phosphorus. So without much delay, so I would like to talk about the first topic. So the first topic talks upon the process of producing YAG cerium based on microwave time. So these are the key points. We're talking about microwave combustion process to produce the YAG cerium based process. I mean the YAG cerium based phosphorus. And the next one I'm talking about is the same microwave combustion, but this time we are talking about the key parameters of different fuel sources. And the last topic of the paper which I have here is based on the impact of annealing temperatures to produce YAG cerium based phosphorus. So the most key important element here what I would like to discuss on these 3 papers are that these 3 papers are basically having the same fundamental and in fact the same methodology process flow on producing this phosphorus. So that's the interesting topic, and basically we know where these 3 phosphorus are produced in fact in USM. These 3 topics are actually papers which is being produced in USM based on PhD students in INOR and also from the School of Physics. So these 3 papers is enabling us to understand further, especially on the impacts or the key structures and the differences between producing the YAG cerium based phosphorus. Now, YAG cerium based phosphorus, what are they? What are these element actually? So basically, these are yttrium aluminum garnite. So let me repeat that again. These are yttrium aluminum garnite, which are cerium doped. And how do they look like? Basically, these are the pictures here which I have for you here. These are the picture which I have on how does a traditional or a common YAG cerium doped phosphorus looks like. Basically, they're yellow, and this phosphor component is a very common, I would say a very well known across all the LED producing industrial guys. And in fact, to rest of the team members of 504, I would like to inform you that in fact in Osram we also do use this phosphorus. Maybe if you come and see me, I'll explain further more on what the nomenclature which is being used in Osram for this phosphor system. So yes, so we have a yellow phosphor mixed with a blue LED, and we have white light producing LEDs with the excitation of the blue towards the yellow phosphor system. So this is the phosphor, I mean these are the LED system works, and Yes, without much ado, so let's go on the next topic. Yeah. Now, on the first journal, which I will present today, is based on the topic of the effect of microwave time on the structural and luminescent properties of YAG 𝐶𝑒3, prepared by microwave solution combustion synthesis. Now, the key point which I would like to stress here is microwave time, and here we'll be studying and looking forward on the outcomes on the structural and their luminescent properties. So we are covering on microwave time and how does it impact towards the structural and the luminescent properties. Yeah. Okay, so in this page, I would like to talk about the executive summary for my journal 1 today. So the microwave solution combustion, or MSC, is a synthesis which is an attractive synthesis method to produce luminescent phosphor materials. This combustion reaction triggered by the interaction between microwave radiation and reducing agents or fuels can be produced high quality nano-sized materials. So when we discuss here high quality nano-sized materials means the phosphor systems. Now in this work, yttrium aluminum garnite, or YAG, which I'll be mentioning very much further, is doped with 0.3% mole of cerium, or 𝐶𝑒3+. Now it's synthesized with the MSC method, or the microwave solution combustion method, and later fabricated with the blue LEDs to generate white light. Now the effect of the different microwave time, which I will discuss further in the next page, will give us an impact towards the structural, morphological, and the optical properties of the phosphor materials are investigated. Now, results showed that the crystallinity of the YAG serum was improved when the microwave time is increased, and the phosphor powders have exhibited porous and coral-like morphology, which signifies that precursors materials have successfully undergone crystal grain growth from the combustion process. The luminescent properties of the YAG serum was due to the occurrence of an electronic transitions from 4F ground state to the 5D excited state. So here we are looking back at the subjects from 501 and 502, which explains very much on how does an LED works with the electron transition from the 4F ground state moving towards the high state of the 5D. Now, moving forward, the fabricated white LEDs have shown a higher emission intensity around a yellow region, which is achieved when the microwave time is increased. In this page, we look upon the methodology or the methods which is being used to produce this YAG cerium doped phosphors. So the pictures which I showed you here from this page, the most important is that I would like to highlight is these three precursors which I'm highlighting here. These materials are basically this yttrium nitrate, which produced from Sigma Aldrich, the company which produces it, which has a composition of 99.8% of yttrium nitrate, mixed together with aluminum nitrate of 98.5%, and also mixed together with cerium nitrate, which has 99.99%, which is a very high concentration. Now, these precursors which are highlighted here are mixed together in a beaker, which you see on a picture here. Now, these precursor materials are mixed together in a beaker with distilled water, and they are mixed with a certain percentage of ratio, which I mentioned here. Now they have a 0.3% mole of the cerium, and these three materials are mixed together under a percentage of ratio loading, and they are mixed in the deionized distilled water. And what you see here on a picture is basically how the process looks like, which they mix it in this ionized distilled water and being stirred for 15 minutes under 60 degrees C. I will share a video in a bit on how does this process looks like. And once we complete this process, this mixture of precursor materials are also further added on the urea fuel. Now this is the urea fuel which we have here in the green bottle. This urea fuel are then further added, and again this mixture is again being stirred for another 15 minutes for 60 degrees C. Now, once we have completed this stirring process with all the precursor mixed with the fuel agents in the beaker, this beaker mixed with these elements or these ingredients are and then move forward to the combustion for inside the microwave oven. Now the combustion here, which is the main key aspect of our paper today, or this journal 1, which discusses on 5, 10 and 15 minutes of time lapse, time parameters which is being used to produce these phosphor systems. So we have the mixtures in the beaker, and then we have this beaker moved into the microwave oven as shown in the picture here. So once we place this in the microwave oven, we place it in 3 different times. So the specimen is broken into 3 different times between 5, 10 and 15 minutes. As I have mentioned in this previous page, here is the recording of how the stirring and heating process which is being done. So
in 60 degrees?
Yeah, 60 degrees.
How you know now it's higher lah, now it's 70 lah.
Yeah, so this is being stirred under 60 degrees for 15
what
minutes.
I do is, if sometimes it get a little bit higher, I will transfer it down.
This is how it looks like.
And let the temperature drop, then I put it back. Yeah.
So you already mixed the precursors, not yet?
Yeah, already mixed everything
Inside here.
Okay. Now, once we have completed our process from microwave combustion synthesis with the given time of 5, 10 and 15 minutes, the next process is being continued with the phosphorus, which is completed the microwave combustions, is further annealed at 1050 degrees for 5 hours in air. So the picture which I'm showing you here, which I'm highlighting here, is this hot furnace which is available in our School of Physics in USM. You can find it in the furnace lab, and here the phosphorus which is completed the microwave combustion for 5, 10 and 15 minutes is further brought into annealing of 5 hours in air at 1050 degrees C. Now the question comes on why do we really need to do further annealing when we have already completed the microwave combustion synthesis process. Now, to answer this, these 3 papers or the 3 journals which I will be discussing today, on all 3 journals, you will basically see the similar process methodology and methods which is being used. To give you all a brief understanding, these 3 journals covers upon the similar methodologies and the similar process, with in fact under a similar lab equipment being used, but under a different time sets and also under a different key parameters and a different and a slight modification of process parameters to understand of producing this YAG serum based phosphorus. So here we have the hot furnace which I've just mentioned, and the reason why we do this is because we would like to remove the impurities. So this is one of the reasons why we have an annealing. So my 3 papers or the 3 journals which I've mentioned do have these process systems, and the reason why we have an annealing is basically to make sure or to produce a high concentration of YAG cerium doped phosphorus without producing of impurities. Okay, and once we have completed the annealing process, the process move further on upon these upon these phosphor systems being mixed together with a silicon and dispensed on an LED package. So this is how does it look like of silicon mixed with phosphor being dispensed on an LED package. And moving forward, once we have this package, it's further being cured into a temperature curing oven here, and it comes with a temperature curing profile. So they have a temperature curing profile based on the silicon which is being used here. So here we are talking about a silicon which is being cured for 5 hours to produce a finished product. And this is how it looks like for a finished product here. So an LED together with a phosphor system being produced with into a package, an LED being produced together with a phosphor system, as how we see here. And here is what I'm showing you here, highlighted, is the COB package, which is very common on the LED market we have today. And once we have this LED package, now this LED package is further being running into characterizations. And before I go further into here for characterizations, the characterizations are also done on a system level once we have completed the annealing process. So characterizations of the phosphor powders completing annealing process based on 5, 10 and 15 minutes are also being characterized for some portions, and some of the portion moves towards the mixing of silicon and the final one of the LED package here, like I've shown. Okay, and this is how the methodology is being done overall for producing a microwave combusted YAG cerium based phosphor under a given different times of 5, 10 and 15 minutes. So this is the methodology which is being done. Okay, now discussing in this page is very much on the results and discussions from the journal 1 talking about the microwave time towards producing YAG cerium phosphorus. Now in this page we will discuss one of the topics here, which is the XRD results. So it comprises from figure 1, which you see the diffraction peaks of between 5 to 15 minutes, and in figure 2a shows upon the outcomes from the XRD, which is giving us the updates on the lattice parameters and also the crystallite size. Okay, and here I'm highlighting these two topics which we will discuss further. Now from this experiment we notice that the results show very much that if we were to do a microwave time between increasing from 5 to 15 minutes, we see that the diffraction peaks become more intensified and narrower when it gets into the higher temperature. So that means we see here it gets even better when it's moving towards a 15 minutes time range for the microwave oven process. Now further, when we move towards the annealing process, we do see that this annealing process enables us to get a more pure YAG cerium phosphorus than rather any metastable phases. Now when we talk about metastable phases, we are talking about the producing of YAM and also YAP. Now these are phases of the phosphor which we would not want to have for producing the YAG cerium. So our target here is YAG. So the elimination of YAM and also YAP is important for us to produce a good phosphor systems. Now once all these materials are completely transformed into YAG phases, now it is informed here that the best case to run this would be on an annealing process or a high temperature solid state reaction at 1100 degrees C. Now it is reported in a report from my colleague, and here we see that YAP and YAM phases could anyhow still be detected. Now from this experiment we have seen very well that the microwave solution combustion is able to synthesize high purity without any detection of YAG and YAM. Now that's the good news from this experiment. Now further than that, we notice also the lattice parameter as shown in figure 2a. We see that it's being closer to the target of 12.008 of YAG according to the reference of JCPDS as shown here. If you notice here, 5 minutes you get at about 12.053, and then it goes to 10 minutes, which is getting even lower, 12.049, and 15 minutes at 12.038. So once it gets lower, we are seeing 12.038 here coming closer to 12.008 here for YAG. Now the question comes, why did not we achieve the 12.008? The answer comes simply, it's because we are targeting to produce the cerium doped. Now cerium doped means we do have some incorporation between the cerium doped towards the yttrium. Now this gives us and incorporation, which gives us a value of such as 12.038 here. Now, with this change structure, the lattice parameter is what we see as the results here. Now, moving forward, we also know that the 15 minutes time gives us a more better crystal structures. From the value we see from the 2A figure, we do realize the crystallite structures over time from 5 to 15 minutes becomes bigger, and this is very much due to the time of 15 minutes sufficient for the crystal growth to be produced. Now, from here we notice that the YAG doped cerium producing at 15 minutes has demonstrated the best results across all. Okay, these are very much the XRD results. Discussing further on the next results and discussion would be the FE-SEM characterizations being done. Now, from here we do see figure 3, which is being showed between A, B, and C. So A here discusses on 5 minutes, B is 10, and C, which is 15. So here what I would like to discuss is that when we do see 15 minutes to be our target, which is correlating very much on the XRD pattern that we are seeing. So meaning we do see very much of a coral and porous crystal-like pictures as we see here on figure 3. But very much of this picture becomes intensified when it's microwaved at 15 minutes. Now moving forward, we see that this effect is very much informing us the effect of longer microwave time to promote particle growth. And this particle size obtained from the FE-SEM is agreed that it's calculated from the XRD pattern. So we see this pattern of the FE-SEM, which has more pores and more coral-like structures, and these structures is basically informing us that there is a growth of these crystallite structures. In this slide, we will discuss the EDX characterization which is being done towards the 5, 10, and 15 minutes of the microwave time. Now from here we notice that the S1 would be the 5 minutes, all right, the S2 is the 10, and the S3 is the 15. Now from here what I would like to say that there are definitely a deviation between the target of 0.6. Now the EDX we needed to achieve 0.6, but looking at this slight deviation, we do believe that there is a metastable strain which is still available. We do believe these metastable phases are still available, and also we believe that the cerium dopants are also incorporated into the YAG, which is why it's causing us to have the differences from the EDX results. Now, as I have mentioned earlier during the XRD discussion, this is one of the reasons why we see there is a possibility that the YAG incorporated with cerium may be one of the reasons why we are not getting an accurate or an exact 0.6 target here. So if you were to look at the values, these are still alright, I would say. And the most important is that they have the presence of the following elements which is being targeted here. Now looking at the final results and discussion, in this page we shall discuss on the electroluminescent properties from the phosphorus mixed with the blue LEDs. So as I mentioned in the methodology, the final process we shall look at is by mixing this phosphorus onto a blue LED, and it is being characterized under electroluminescent measurement systems. So from here I would like to mention that we have a targeted now figure 4 as we stated here, figure 4, which is looking at the CIE chart at below here. Now from here we know that A is 5, B is 10, and C is 15. So from here we can say that the YAG cerium, which is being produced at the longest microwave time, is moving towards a warm white color region. Now, when we say this, I would say that it's moving towards a warmer white color region, which is considered as good in the industry for a white LED. Now, when we combine the phosphors together with the 465 here, it's very well represented in the spectrum measurement seen in figure 5 here. Now, when I talk about 465, it really looks into the peaks of the blue, which is representing at 465 LEDs. Now, we know the 5, 10, and 15 are all having the same 465s, but the most interesting aspects to look is that we can able to detect the yellow emission spectrum of between the 5, 10, and 15 differs across each other. Now, the good news is that we see 15 minutes is representing the best, which is giving us one of the highest intensity of yellow spectrum, which gives us a very nice color of C here, which I mentioned. So it moves towards a warmer white region. Now, this gives us a very good indication that the longer the microwave time, the more yellowing spectrum which is targeted to be produced from the YAG cerium is being achieved here. Now, this is the important thing which I would like to mention between these two figures. So the longer the microwave time, the more higher and better producibility of the YAG cerium based phosphor systems. So this is the last results and discussion, and I would like to end that to say that these phosphor systems indicates that white light can be produced, which we are seeing in the CIE chart in figure 4, and this can be incorporated by the cerium atoms, which is incorporated together the YAG lattice, contributing towards more of the yellow emission systems. So the microwave time at 15 minutes gives us the opportunity for the cerium atoms to be incorporated into together with the YAG lattice to give us a more better yellow emission. Yeah. Okay. On my next topic on Journal 2 is synthesis and characterization of YAG cerium doped phosphors by microwave-induced combustion synthesis with different fuel sources. So in this title, the key elements which I would like to mention here is back again. We are having the YAG cerium dope, as I've mentioned previously, and we are still using the microwave combustion synthesis method. And something interesting or something new in this topic right now would be very much on the different fuel sources. So here we'll be covering with different fuel sources, discussion on different fuel sources to create the YAG cerium doped under the microwave induced combustion synthesis. In this page, we will discuss on the executive summary for Journal 2. White LEDs have been produced from the combination of blue LED chips and phosphor converter. In this work, considerable amount of yttrium aluminum carbonate or YAG phosphor powders doped with 0.3% mole of cerium have been synthesized through microwave-induced combustion synthesis, or in other words, MICS, with different fuel sources such as urea and mixed fuel of urea plus glycine. The effects of these different fuel sources is coming through from the crystallinity, structure, and luminescent properties. We will also see the CIE chromacity, which is characterized and studied with the XRD method, the FESEM, and the EDX, together with the EL measurements based on the 1931 CIE chart. Now, the higher intensity can be observed from the sample prepared for the mixed fuel technique, and in contrast, the experimental enhancement in the aforementioned properties is demonstrated by the WLED synthesized using mixed fuel techniques. So here the summary states very well that the mixed fuel works better than the single fuel system. And WLED means it's white light LEDs, as I've also mentioned in my previous journal. Now moving forward, also with the similar methodology like I have mentioned on the journal 1, the journal 2 also comprises the same methodology. In this paper, the precursors, the similar precursors as I'm highlighting here, is also being used and mixed together with distilled water and stirred for 15 minutes at 60 degrees C. And after this process, the key element process or the key element target which we need to look here would be this process step, where we will break it up into S1 for urea and S2 where it's a mixture of urea plus glycine. So these are mixed together into the beaker of the deionized distilled water, and from here we will continue for another 60 degrees C for 15 minutes. And as similar to the journal 1, the same beaker is also undergoing the combustion microwave oven. Now the previous journal states on 3 setting temperature, but here the journal states of a setting temperature of direct 30 minutes for both S1 and S2 samples. Continuing from the earlier methodology, so moving forward, the samples which is completed for the microwave combustion further goes for annealing process with 1050 degrees C for 6 hours in air, and then it's further mixed with silicone on LED packages, like I have also mentioned on my previous journal 1. It goes through the same process step, and also it goes through the curing with the temperature profile provided based on this silicone, which is also 5 hours. The end product is always the COB based WLEDs, which we see in the picture here, and also it undergoes the same characterizations from the powder base, from here, and also from the final fabricated LED. So we have 2 characterizations provided here. Now this chapter we will discuss much on the results and discussion, covering on the XRD characterization. The XRD is being done between S1 and S2 samples, and basically from figure 1 we do see upon the outcomes of the XRD showing us upon the YAG, YAM and YAP phases. As we can see the peaks here, 1, 2 and 1, 2, both on S1 and S2. Now the most important is that we have also detected the YAG phases, which is 1, referencing to the JCPDS file, and also we notice that both has this YAG phase and they also have the YAP and YAM phases. But the most important thing is to note it here is that the S1 has more peaks of YAM as comparing to the S2, which is the mixed fuel ratios, indicating that basically this mixed fuel has higher temperature decomposition. So the S2 has a higher temperature decomposition to form the YAG CE phosphorus. Now all these metal nitrates achieve higher temperature exothermic reaction and improve crystallinity compared with S1. And from the results, we see that the crystallite size of S1 was smaller than of S2, which tells us that the growth of the crystals in S2 is better. And we look upon also for the S2 having a more agglomerate and more increased in size, and this gives us that very much the mixed fuel technique suggests that the change in particle size and crystallinity are dependent upon the amount of urea and glycine used, OS2. Now we go to the second results and discussion for journal 2, which is the FESEM. So here we have the picture on the left hand side, which is the S1, and on the right hand side, which is the S2. So from the FESEM pictures, we can see that the S1 has larger pores compared to the S2, which I would highlight here. And from here, we understand that during the MICS, or the microwave induced combustion synthesis, it is found that the gases released for each mole or solid product is formed. These gases escape through the pores between the particles, and these pores are related to mass transfer in mechanism depending on the temperature during the exothermic reaction. So at higher temperature, the exothermic reaction to occur, the pores will become smaller. So meaning at higher temperature, the pores will become smaller. Now this is seen very much in S2, as I'm highlighting here. And whereas the reaction at lower temperature, the pores would become larger. So at lower temperature, the pores become larger. And this is seen in S1. Now moving forward, we can understand from this case that S2, the smaller pores, which reflected the diffusion, is the main mass transfer mechanism due to higher temperature by mixed fuel during MICS. Now moving to the third characterization with results and discussion is very much on the EDX of the samples S1 and S2. It is noted that the atomic percentage of O in S2 is much more lower than the S1. Now this is basically explained by the difference of solubility of each element, where O is evaporated better at higher temperature from the S2 due to the mixed fuel ratio, while the S1 has the elements much more smaller if we were to look at aluminium, yttrium and cerium as compared to the S2 of aluminium, yttrium and cerium. Now this explains very much that the atomic percentage of Ce can be caused by the reduction of metastable phases of YAP and YAM, like mentioned in Journal 1, which leads to higher purity of the YAG doped cerium. And this happens in the S2 samples, which a mixed fuel ratio of urea and glycine. Now looking at the final results and discussion from the electroluminescent measurement, the study of the performance of the WLEDs of all color properties of the white light emission from the S1 and S2 have been tabulated in table 3. So in table 3 here, basically it shows that the S1 is more of a cooler white region, which is nearer to the bluish region, while the S2 is on the warmer white region of 5000 kcct, as shown in the CIE graph of figure 4. Now from here it is understood that the figure 3, which shows the spectrum of both S1 and S2, represents very much of the yellow emission peaks, which is very much seen for S2. So the transformation or the producing of YAG CE with yellow emission peaks works well with S2. Now this gives us a very good color range as shown in the CIE graph in figure 4. Now, as I've mentioned in Journal 1, this is the similar study which basically says that the S2 under the mixture of urea plus glycine gives us a better transformation of YAG CE phosphorus, which gives us a very good yellow emission properties. Now to go on our third journal, which is the final journal of this assignment, this topic covers of the effect of annealing temperature on growth particles of YAG CE, phosphor and white light chromacity values. So as compared to the two journals mentioned beforehand, this journal discusses very much of the annealing processes towards the YAG cerium phosphorus. So as I've highlighted here, and here we will discuss further on the impacts of the annealing towards the YAG. Okay, in this page we will discuss the executive summary for Journal 3. I will not touch the first paragraph, which basically represents very much from Journal 1 and Journal 2 methodologies. Here I will further discuss much of the annealing processes in paragraph 2. It is understood that the 1050 shows a better crystallinity structure, chemical composition, luminescent properties. So from here, it shows that the results obtained for YAG cerium sintered for 5 hours under 1050 degrees C does produce good crystallinity with pure phase, low agglomeration, and spherical shaped particles with a strong yellow emission, offering cool white LEDs with tunable correlated CCTs, comparing to those sintered with 850 and 950 degrees C. Now moving on the research methodology, the same process steps as mentioned from Journal 1 and Journal 2 is still mentioned here. We have the same precursor materials, which is mixed with the following composition. It is still mixed with the deionized distilled water, where we have the urea fuel mix under a percentage ratio, and it further goes for a stirred of 15 minutes 60 degrees C, and finally it goes into the MICS process for 30 minutes. Now to continue further with the research methodology, here we do see the most important key aspects from this Journal 3 will look into the annealing of 3 setting temperatures of the phosphor systems. So here we will look at 850, 950 and 1050 temperature on the annealing portion. The rest of the process step is still the same. We have the mixed phosphorus dispensed with the silicon together on a LED package. Now, one thing I have missed out is this is how, which I'm circling and highlighting in the picture here, that shows the phosphor mixed with silicon. Now, this is how it looks like. Now, moving forward, this phosphor silicon is and then dispensed on the LED package, where finally we cure it in the temperature oven profile, and finally we have the full WLEDs or COBs, which I'm highlighting here, which is undergoing the characterizations, and together we have the 3 phosphor powders, which I'm highlighting here, still going to the same characterizations. Okay, let's look at the XRD results on the Journal 3. So from here we can see that basically from the highest temperature of 1050 produces a very good YAG CE phosphor system as compared to the other temperatures. So this gives us a very good results showing that we can achieve the targeted YAG CE production with the synthesis or the sintering of 1050 degrees C. And if we were to look at the crystallite and also the lattice parameter, we do see that the 1050 degrees C shows us nearing to the 12.008 on the lattice parameter, and also the biggest crystallinity showing the growth of the YAG CE sintered at 1050. And now looking at the FESCM, if we were to make a comparison between the previous 2 journals, I would say that very much the images produced in the SCM does not differ much with whatever which we have done with Journal 1 and Journal 2. The information very much we know is that we get a flaky, thin platelets to be seen in this journal. But also we do see also there's this cracks and pores which is being formed. Now, it's very important that it is being informed that part of the methodology here is that, which is not stated in this paper, is the usage of pestle and mortar. So they have this process where they use this pestle and mortar, which is a very much on the usage of manual handling from the human sense, or human centric, I would say. Now the thing is, when we have this pestle and mortar, means we are looking at doing what you call a process which is really dependent on the human energy and the human force. So if you were to compare with the human energy and the human force between person to person, that may differ. So the formation of this Fe-SEM is very much on how much of energy, force, and time which is taken to be crushed, where these phosphors are being crushed after the microwave, and then they are submitted to the annealing. So the end product here may differ again. So you may have you can see the structures which is very much differing upon human to human strength, I would say. And now on the electrolumination measures, here we see the spectrum for the 1050 looks quite good. In fact, when we look at this CX-CY graph in the CIE chart, we see that in fact parts which is measured at 1050 is showing us quite a nice positioning in the CIE chart. This drops into the I would say it's much on the cool white, in between the warm white and the cool white region of 5000 K CCT. And if you were to look at the spectrum, we see that very much the yellowing impact is being seen. So that means this tells us a very good excitation on the blue light towards the white light, as there's an impact of the phosphorus, yellow phosphorus being used. So this gives us a very good indication that the 1050 works well for starters, and the results from here shows that yes, we are good to go. Now here I have compared on the XRD. So part of this topic talks upon the overall comparisons, and I've used the XRD as a topic of comparison. So here I've tabled up upon the three journals, the journal 1, the journal 2, and the journal 3. So here we do see that the XRD shows the crystallite size. Now the thing is, I cannot compare very much on the of course we do see the crystallite size is bigger on the first two journals, but since it was done at the different position of time with the different mixing ratios and the different equipments, and with depending on time, human factor as well, so I would say that very much on the XRD we see that for example the journal 1 on microwave time, we see that longer time with microwave enables sufficient time for crystal grain growth. This is the important topic, and microwave is able to give a quick results. So yes, for journal 1 it states very well that microwave is able to give a quick results within 15 minutes to show the YAG diffraction. So this is another topic. And on item 3 we see anyhow there is also YAP and YAM which is being formed, means they are metastable phases are still being detected. So this is what we see. And on the second journal we see that all metal nitrides achieve higher temperature exothermic reaction. So this mixed fuel ratios with glycine is giving us a very good exothermic reaction as compared to a single fuel. And on top of that we do see that the crystallinity size is increasing when we use a dual fuel system. Okay, and the last one we see on the topic for annealing temperature growth on the YAG formation, the YAG-CE formation, we see that it helps to remove the YAP and YAM, this is for sure, for the annealing. And we also see that the annealing at higher temperatures at 1050 samples shows that it shows purely of a YAG-CE formation. And this is good, it improves the size and also it gives us the better lattice parameters. So overall, to conclude upon all three journals, the interesting thing is all three journals show us on the formation of the YAG-CE. And this is something we have been going through. So upon this, I would say that the journal number 1, we see that yes, with microwave time, we know that there is no YAP and YAM in the XRD pattern seen at 15 minutes. And the phosphor produced were approximately spherical shape, and they have these porous-like structure. Yeah? So 15 minutes is sufficient for the microwave based on journal 1. Now on journal 2, it shows that YAG-CE phosphor with mixed fuel show us the best crystallinity, but anyhow there's a detection of YAP and YAM metastable phases. And journal 3, we see that YAG-CE pure phase is formed in 1050 degrees C. And this annealing temperature is now showing us the best without any metastable phases from like journal 2. So these are the overall conclusion upon journal 1, journal 2, and journal 3. Okay, now looking on the summary for me to choose upon the 3 journals and which is the best would I prefer, I would say would be journal number 3. So why I choose journal number 3? Simple enough, when I were to look upon the following results, for example the XRD here as example 1 here, it states that very much in journal number 3 tells me that the XRD peaks produces YAG cerium phosphorus as compared to journal number 1 and journal number 2. Now, journal number 2 tells me clearly that there were detection of YAP and YAM metastable phases, while journal number 1 does not tell me there is a YAP and YAM. Instead, the statement states that yes, there were no YAP and YAM, but I could not find any of the numbers of YAP and YAM peaks here. So if I were to compare both peaks, it does not tell me if there were 2s and 3s and 1s as compared to the journal number 2. So this is the reason why I would still state that journal number 3 would be my preferable journal and the one which I feel the best. Now, further topic, I would say that comparing to journal number 2, the final product after microwave with single fuel at 30 minutes from annealing tells me the finished products not producing more yellow spectra needed as per standard YAG function. So from comparing to journal number 3, which we know very well it's achieving the YAG cerium spectrum and with the XRD results, so compared to journal number 2, but journal number 2 tells me another details which I further analyze. Now this is something interesting that I managed to check, is that this glycine alone fuel was also done in other papers. Now based on these papers, we do see that this glycine create a lot of this carbon content as shown in the picture below. So below here what you can see is basically an after finish microwaved YAG cerium mixture as compared to the standard, which is giving us more of a whitish yellowing effect as what I see here, the black version. So there is a important statement to state that there is a possibility that the glycine do produce a lot of carbon content, which there is a possibility that there is a need to decompose this carbon content further with annealing process. So there is a possibility that glycine mixed in urea, which we do detect these YAP and YAM metastable phases. There's a possibility that we need further annealing to remove these metastable phases and these impurities. So this is giving us a good indication that anyhow in the journal number 3 gives us the best results. And moving further, this is the last one I have, which is really telling me why I choose upon journal number 3. So the first picture here I have is a commercial version. Okay, the second one is journal number 3, and this is journal number 2, and this is journal number 1. Now from out of the commercial, I do see that the YAG, this is a YAG cerium phosphor commercial. We do see that very well the spectrum comes nearest to journal number 3. If you notice, for 1050, the spectrum of yellow impacts comes close with journal number 3 as compared to journal number 2, which is telling me very much that it is giving us, there's a problem here where the blue peaks immediately turns to green. So this is not a very good peak data or spectrum, And the last one, as compared to the third, journal number 3, journal number 1 has a lower peaks of and a shorter distribution of the yellow peaks as compared to journal number 3. So journal number 3, I would say, is the best. It has nice yellow peaks, and it has also a broader yellow peaks and high peaks as well. So this is the reason why I choose journal number 3. Okay, so this is my final slide, and to summarize overall on the journal number 3, which I've chosen as the best. So hitting the target of warmer CCT as compared to other journals. So journal number 3 is seen hitting the target CCT as compared to the other journals. So the reason why I say this is that I made a comparison upon the CCT targets. Yes, we do see that journal number 3 gives us a 5,000 range within the cool white to warmer white region, and there is also journal number 2, which is also hitting better than this, and the last one is journal number 1, which is going to the cool white region. Now, but anyhow, journal number 2, we know that there is a YAP and YAM phases. Now, in a LED structure, it's important for us to know the phosphor systems used is able to give us a longer lifetime, which is very important, especially for the solid state lighting. So in the detection of YAP and YAM metastable phases, this may lead to early degradation. So you may have degradations issues in the later stage, especially towards the final LED package. So this is one of the reasons why I choose journal number 3, even though they have a CCT which is slightly higher than the journal number 2. Now, overall, I would end this assignment. I would say that overall, we do see that there is a neediness on the following that fulfills to produce a good YAG cerium phosphor with the combustion, microwave combustion, and annealing process. Now, the first one is that I believe that we need to have a microwave combustion which runs above 15 minutes and an annealing process which works above 1050 or more. This is my 2 statements which I would say overall gives me the reason why that to produce a YAG cerium doped phosphor is able to be done with the best purity level under the following situations. Okay, so thank you everybody. I hope I did not bore you, and I hope you had a good time understanding on the 3 journals which I've just presented. Thank you very much, and I hope if any questions you can come and call me or do meet me and discuss with me personally. Thank you. Thank you.